Okay, so good morning, everyone. We'll continue with the lecture. And yeah, so these are the topics for today. Let us dive into it. So we were into gamma function, and we spent some time in understanding gamma function. And now I would like to define the gamma distribution. Okay, that was the reason to define gamma function. So this is gamma distribution now. With parameter alpha greater than 0 and lambda greater than 0, and we denote it like this. Okay, so this is like x follows a gamma distribution with parameter alpha and lambda if the PDF is given by this. Okay, so it looks a bit complicated, but this is the PDF for and it's defined for x greater than 0. Okay, so the range is from 0 to infinity, and as a special case, if alpha is 1, if you substitute alpha equals to 1, you will see that the PDF will become this. Okay, so and this is the familiar exponential distribution. Okay, that you may recall. Okay, we have done exponential distribution. So gamma 1 and lambda, that is exponential of lambda, and one of the result is like if the sum of n independent exponential random variable is a gamma random variable. Okay, so this is something you may try to prove. Okay, or maybe you can look up in some textbook. Okay, so I'm not going to do this. Okay, so what are the properties of gamma? Okay, these are like distributions. Okay, so what are the properties of gamma distributions? For instance, the integral of the PDF from minus infinity to infinity, we know that for any distribution, the integral of the PDF must be 1. Okay, so minus infinity to 0 is anyway 0. So that's why integral is now from 0 to infinity must be equal to 1. Expectation of x must be alpha by lambda, and variance of x must be alpha by lambda square. Okay, so these are the properties of the gamma function. So we can like try to prove these properties. So the first property is that integral of the gamma. So which is so the first property is integral 0 to infinity fx x dx must be equal to 1. So this is what we have to prove. And fx x, if you recall, is lambda to the alpha x to the alpha minus 1 e to the minus lambda divided by gamma lambda, right? So this so we have to prove it's 0 to infinity, and it was lambda to the alpha x to the alpha minus 1 and e to the minus lambda x. Okay, and in the denominator we had gamma alpha, and this is dx, right? So this is so we can take the constants out, right? So this is like lambda to the alpha and divided by gamma alpha, and then this is integral 0 to infinity, and then what is remaining is x to the alpha minus 1 and e to the minus lambda x dx. Okay, so we can take the constant out, and if you recall, what is this term here, right? So this term is this term we recall property 2, right? So we recall property 2. So recall property 2 of gamma function. Okay, of gamma function, and that was 0 to infinity x to the alpha minus 1 e to the minus lambda x dx, and that is gamma alpha divided by lambda to the alpha for lambda greater than 0. Okay, so this was the property 2 that we proved last time, and this is what we try to see from here, like can we express it in this form? Okay, and it seems to be exactly in this form. So x to the alpha minus 1 e to the minus lambda x, this is exactly this term here. So this must be gamma alpha by lambda alpha. So this, let us say, is star. So continuing from star. So continuing from star, we have lambda to the alpha divided by gamma alpha times gamma alpha divided by lambda to the alpha. Okay, so they get cancelled. Okay, and we get 1. Okay, so this is what we were supposed to prove. And so this is done. Now expectation of this is alpha by lambda, right? So expectation of so this is the second one. So expectation of x is alpha over lambda. So let us find out expectation of x. We apply the definition, so which is x fx x dx. So this is how we find expectation. It's 0 to infinity. Okay, and this is 0 to infinity x, and then we substitute the we substitute the PDF of this, right? So if we substitute the PDF of this, this is the PDF, right? So we put this value here. So lambda to the alpha, x to the alpha minus 1, and e to the minus lambda x by gamma alpha, and this is dx. Okay, so in this case again, like we will pull out the constants. So gamma alpha, and in the integral inside we have x times x to the alpha minus 1 and e to the minus lambda x dx, and this is equal to lambda to the alpha divided by gamma alpha, and this is integral of this, and then here we observe this x, so this is x to the alpha e to the minus lambda x dx. And okay, so so what is this now, right? So remember that if we use property 2 again, here it was alpha minus 1, so it became gamma alpha by lambda alpha, but here it's alpha. Okay, so it will be like gamma alpha plus 1 by lambda alpha plus 1. Okay, so we use property 2. So using property 2 of again the property 2 of the gamma function, what we can write is this is lambda to the alpha by gamma alpha, and this is gamma alpha plus 1. Okay, so this is gamma alpha plus 1 divided by lambda to the alpha plus 1, and this is, now again we know that gamma alpha, this is property 3, right? Now using property 3, we know that gamma alpha plus 1 is alpha gamma alpha, right? So this is like lambda alpha by gamma alpha, and this is like alpha gamma alpha divided by lambda alpha plus 1. Okay, so this this becomes how much, right? So lambda will be there in the denominator, and gamma alpha gets cancelled, so this guy gets cancelled, and lambda will be there, so this is alpha by lambda. Okay, so this is the required result that we needed. Okay, so this is the 2. Okay, so that's done, and the third property that we need. Okay, so the third property that we need is variance of x is alpha by lambda square. So variance of x, what we really need additionally is expectation of x square. So if we continue like before, so this is like x square fx x dx, and this is 0 to infinity. This is x square lambda to the alpha by gamma alpha, and x to the alpha minus 1 e to the minus lambda x dx. Okay, so this will come out to be how much? So if we do simplifications and so on, so what we have here is 0 to infinity, and x will be x alpha plus 1 now, and e to the minus lambda x dx, and this will be lambda alpha by gamma alpha, and this is gamma alpha plus 1 by lambda alpha plus 1. Alpha plus 1 is already alpha plus 1 there, so it's alpha plus 2 by lambda alpha plus 2. Okay, and using the property that gamma alpha plus 2 is alpha plus 1 times gamma alpha plus 1. Okay, and then yeah, some alpha gets cancelled. So eventually, after all the cancellations, what we will get is alpha plus 1 by, okay, lambda squared. Okay, so after cancellations and everything, Now from here, now we can the variance now we know is so variance of x is expectation of x square minus expectation of x whole square. So if we do this, then this is alpha plus 1 by lambda square minus alpha square by lambda square, which should come out to be, you can check this, we should come out to be what we were asked, alpha by lambda square. Okay, so this is something well, it's already alpha square gets cancelled, right? So this is done, right? So we have proved all the three properties of the gamma distributions, right? Okay, so now let us look into so before we wrap up, so this is kind of the wrap up of the continuous distribution, and I will do some selected examples, okay, and then more on this you will do it in the assignment. So here, like I may do some selected examples on this, and then like we can wrap up this part as well. Okay, so let's see. So if so this is the uniform distribution, and x is log of 1 minus u, and then so that the exponential of x, so that x will follow the exponential 1. Okay, so this seems to be rather straightforward, I would say. Okay, we can already do something. Let us try this, and if I have some time, then I will come back. Let us try this actually. Okay, here it's like I'm transforming again x, and this is a normal distribution case, and y is some function of x here. Okay, and the problem is find expectation of x greater than 1, probability x greater than 1, probability that y greater than -2 and less than 1, and so on, and probability. So these are the probabilities that we have to compute, and we are given that x is a normal distribution with mean 2 and variance 4. Okay, so let me do this quickly. Okay, so first question is probability that x is greater than 1, right? So probability that x is greater than 1. So this is the solution to A. Let us say probability that x greater than 1. So remember that we had some results with the normal distribution, and what was those results? Like if we are given a normal distribution, so a standard normal that we know, so the standard normal distributions are given by like this, 0 and 1, right? So this is the mean is 0 for standard normal and variance is 1. And if we are given a arbitrary, like just the normal, not really the standard form, okay, so this will like look like this. Okay, so this is not really a standard, this is just a normal. Okay, so so let us write down first. Okay, so for the given normal distribution n and it's like mean is 2 and variance 4. Okay, so mean is 2 and variance 4. So here, like we write down what is the mu x. Mu x is 2 and sigma x is 2. Okay, mu x is 2 and sigma x is 2. And probability that x greater than 1 is same thing as, okay, so let me do this. Okay, so this is 1 minus probability that x is less than equal to 1. Okay, so this is 1 minus, now I can substitute this by the CDF. Okay, so CDF, it's like fx of 1, right? Now we know that we can like we can write this using phi function, right? So we can write this using phi function, but the phi function is like defined for the normal, right? So we need to change this to like normal, right? So 1 minus, so I can use the phi function, but I have to do the proper scaling. So what was the phi function? If I have to use the phi function, right? So what do I have to do? So recall. Okay, let me Control Z. Okay, so recall that probability that x less than equal to a, like for any even like non-normal. So what was there, if you recall? So this results we did, right? So this is like a minus mu x by sigma x. Okay, so these are the results we did. Like this is this thing we are doing scaling because it's not normal, right? So it's a general a normal distribution. So we have to do something like this. If it was normal, then we just do phi of a, okay? Because mu x is 0 and sigma is 1. So if x was normal, then this is nothing but phi of a itself, which is the CDF, exactly the CDF of that. If x is not given to be normal for you, then you have to do this kind of thing, scaling, like shifting and scaling, right? So this is something we have seen before. So this is, we know that this is not normal, so we have to do this here, okay? So if we do that, then this is phi of 1 minus 2 by 2. Okay, so this is 1 minus phi of how much? Minus half, right? So this is like minus 0.5. And we know that this guy, it can be written in terms of 1 minus of phi of positive 0.5. So overall, this is phi of 0.5. Okay, so we can leave it here. Okay, we don't have to, or if the table is given to you, you can look up for this. Phi tables are usually given in exams also, we will give. Okay, or you can leave this here in the exam. Okay. Now the question, second question is find the probability that y is greater than -2 and less than 1. Now the idea again is like simple, okay? So now you can already see we will use the phi function and these things, right? So -2 is less than y is less than 1, okay? Okay. But the thing here is like now this is a question in y, right? So now this is a question in y. So we have to transform this into y, and we have to ask which normal is y, because the way we are doing this changes, it will guarantee that y will still remain normal, right? So this is also result we did. Okay, so let us see what will be the y, the mean and the variance of y, right? So since y is 3 minus 2x, then we have some previous results. So previous result, okay? So from previous result in the previous classes, what we know is that that mu y, or you can like explicitly compute it here as well, right? So what was the previous result? If y is of the form ax plus b, then y is normal with mu x and sigma x square, where mu y and sigma y. Okay, so where mu y is given by a mu x plus b, and sigma y square is given by a square sigma x square. Okay, so this is the result that we have seen before. So this is the result that we are going to invoke here, where a is -2 and b is 3 here. So now you know what is the mean. You know that with this kind of transformations, kind of a linear transformation here, we are ensuring that y will be normal with this. Okay, so this is the result that we know. So this implies that y is normal with, so if I compute this, right, so it will be like a times mu of x. So the mu of x is 2, right? So a is like -2, so -4. And -4 plus b is 3, right? So it's -1. Okay, and sigma y square is a square sigma x square. So a square is like 4. Okay, so a square is 4, and then sigma x square is 4. So it's like 16 total. Okay, so this is the normal distribution. Now what we go back to our question here. Okay, so this is like probability that -2 less than y less than 1 is now. So now we apply the phi function, right? So I can write. So what is this? So in terms of CDF, we know that this is fy y less than equal to 1 minus fy, and y is less than equal to -2. Okay, probability that y lies between a and b. This is the formula in terms of CDF. And okay, so now we apply the phi function here. Okay, so if we apply the phi function using this, because this is still so we have to do this proper scaling with mu y and so on. Okay, so in this case we have y less than equal to a. So in terms of y variable, we have a minus mu y by sigma y. Okay, so we have to do this. So from here, like, we can write down now. So this is like phi of 1 minus 1 by 4. This is sigma y minus phi of minus 2 minus of the mu y, so which is minus 1, and divided by the sigma y, which is 4. Okay, so if we do the calculations for this, right, so it will be phi of first one is like half, right? So this is like 0.5, and then this is like minus phi of this is like 1/4, right? So this is like 1/4. So this is like phi of 0.5 minus phi of 0. Oh, this is like negative, right? Okay, so negative 0.25. So we can leave this here. Okay. Okay, and then the third question is the conditional probability, right? So the conditional probability we have to compute is probability that x greater than 2 and y less than 1. Okay, so how can we write this, right? So this is probability that x greater than 2, and y we can write in terms of x. So this is like 3 minus 2x. Okay, and 3 minus 2x is less than 1, right? So that's okay. So so if we solve the second inequality, then this is the same thing as saying that probability that x greater than 2, and so 3 you go send it that side minus 2, and then you reverse the inequality, so it will be like x greater than 1. Okay, so we solve the second inequality. Now the conditional formula we know, right? So this is like probability that x greater than 2 and, so comma means and here, and x greater than 1 divided by probability that x greater than 1. Okay, so this, the intersection of probability that x greater than 2, x greater than 1 is probability that x greater than 2. Okay, and it's divided by probability that x greater than 1. And this again we apply so this is 1 minus probability that x is less than equal to 2 divided by 1 minus probability that x is less than equal to 1. Now we use the phi function, so this is 1 minus phi of so phi of 2 minus the mu of x. So this is like 2 minus mu x was 2 divided by sigma x was 2. Okay, and similarly here we do 1 minus phi of 1 minus 2 by 2. Okay, so you can leave this here. Okay, so from here it's just like a lookup in the table. Okay, so that's the solution to that. Now yeah, so we can like solve more problems. For instance, here I'm given to find the expectation of x square, right? So it's again it's a normal. Okay, so it's a normal distribution. So and yeah, it's a normal distribution, and we are supposed to find expectation of x. I mean here yeah, so here we can write this guy. I mean, this is not really standard normal yet. Okay, so normal, because in normal, but not a standard normal. So but we always know that we can write this in terms of standard normal. And how we can do that? We can write this as sigma times z. Okay, where z is standard normal. Okay, so this is something we have seen in the previous class again. Okay, so how any normal can be written in terms of standard normal. Okay, where Z is standard normal. So standard normal parameters are fixed. That is Z follows normal 0, 1. Okay, so so we can write like this, and you can check that the expectation of variance of this is just sigma square, because sigma times variance of Z is like 1. Okay, so sigma, the scalar, comes out as a square, and if you take the variance, so that's sigma square, and then expectation will be 0 because the expectation of the Z is 0. Okay, so this is can be written like this. Now, so this implies expectation of the mod of X. Okay, so this is sigma of expectation of a mod of Z. Okay, so this is the absolute value of the mod. Okay, so it's enough to find expectation of mod of Z. Okay, so expectation of mod of Z is 1 by square root of 2 pi. Remember, this is mod of Z. Okay, if it was expectation of just Z, then it was 0, right? Okay, so this is minus infinity to infinity and mod of t, and expectation of minus t square by 2 dx, and t square by, and yeah, so this is an even function. So this is like even function. So we can write this as 2 by square root of 2 pi 0 to infinity, and yeah, so t e to the minus t square by 2 dt. So it should be dt here. And since t is starting from 0, so we can remove the absolute value. So t by square root of 2 pi, so 0 to infinity, and I can write just t here safely, minus t square by 2 dt. Now this is so the integral of this, right? So this integral is like straightforward in this case, right? Because this is of the form 0 to infinity e to the minus t square by 2 d of t square by 2 dt, right? So you treat t square by 2 as some variable, and then e to the minus u du form, and not dt here. Okay, so that's already taken care. So this is like a minus integral of this is minus of e minus u, right? If you do that substitution. So if we go ahead and do that, and this will be 2 by pi, and then this is like minus e minus t square by 2. You substitute back u as t square by 2, and this is 0 to infinity. And this is, if we do this, then the first term is 0 and the second term will be 1. So what will be left with is 2 by pi only. Okay. Okay, so from here we know that expectation of mod of x is sigma of expectation of mod of z, which is sigma square root of 2 by pi. Okay, this is something we have already done. When we were discussing the gamma distribution, I guess, right? So this part is already done. We don't have to do this anymore. Okay, now what I will discuss is so-called mixed random variable. So what we have seen are random variables which can be continuous. In other words, the PDF does not have any jump, or we considered discrete, where we had the jumping values in the CDF, I mean. Okay, so so mixed, we can already like guess there could be a cases where we may have a mix. So we may have a continuous as well as like the discrete part combined. So let us look into this example, and let x be a continuous random variable with the following PDF. Okay, so this is the PDF of x, and we have defined g of x to be this. So it's a function of a random variable with this value. Okay, so let us see what is the CDF of y. Okay, so let us see what is the yeah. So we have done similar thing. Find CDF of a function of a random variable, right? So the first thing we need to know is like range of x. So range of x here we know it's 0 to 1, right? So range of x is indeed 0 to 1, and for x in 0 to 1, what we have is g of x is just x, right? Okay, so it will be 2x, so it's like 2x, so it will be like 0 to 1. So g of x itself will lie between because for 0 to half it's like it's taking like x value, but x value is like is half only, right? Okay, yeah, so it's, yeah, for x 0 to half it's just x, so this means like the gx is between 0 and half, right? Okay, so for x in 0 1, this implies 0 less than equal to gx, so gx is in 0 and half. This is the case because this identity here, right? So it's exactly equal to x. So whatever value x is taking, the same value is the gx is taking. So gx is also lying between 0 and half. Is this the identity? Okay, so that's okay. And what is the range of y, right? So this implies the range of y is so what are the values that y is possibly taking, right? So the first thing we know is that it's taking values from 0 to half, and beyond half it's taking half. So basically all possible values that is taking is from 0 to half. So it's like closed 0 half, right? So 0 and half. So that's the range of y. Okay. So so this implies fy, the CDF of y for, let us say, y less than 0. Okay. So CDF of y for y less than 0 is 0. Okay. So for y less than 0 is 0 because range is defined to be from 0 to half. So that is like 0. And fy is for greater than a half. Okay. So we know that for a random variable, if you go beyond the upper range, then your CDF must identically be 1. Okay, so that is for y greater than half. Okay, so these are like the boundary cases. Okay, we are supposed to find the CDF of y. So what happens at y equals to half? Let us check y equals to half. So probability that y is equal to half is equal to what? Okay, so probability that y is equal to half. When y is equal to half, that's the same when that's when asking x is greater than half, right? So this is the same thing as saying probability that x is greater than half. So, and the PDF of x is given to me. So I will integrate this from half to 1, and PDF of x greater than half, then it follows 2x. So this is like 2x dx. Okay, and this will be how much? 2x squared by 2, so 2 will get cancelled. So this will be like x squared. So 1 minus 1 by 4. This is like 3 by 4. Okay. So that's the probability that y equals to half, and for y within 0 and half, because our range of y is this, so we have to define the possible probability values for y in this range, and that will help us find the CDF, right? So let us check for, so also for 0 less than y less than half. Okay, so let us check the remaining part. The reason why I have done this half separately is like this is the case, like there is a possible jump here. The reason, so you will see that eventually it will be neither continuous nor discrete. There is a jump. There is a jump at half, and otherwise it's continuous. So it's a combination of continuous and the CDF will look like neither continuous nor discrete. So hence we call it mixed. Okay, so let us, in this range, it's okay. It will be like continuous. Let us see why, right? So f y of y in this range is probability that y less than equal to y, and this is same thing as between y 0 and half, because in y between like so between y between 0 and half, this this is identically equal to x, right? So this is like x less than equal to y, and this is right. So y is equal to x in this range half, right? So that's why I just because I'm fixing my range to be half, so I can substitute y by x and less than equal to y. So this became in terms of x. So now I can integrate from, so I have to do 0 to y and 0 to y, and then the PDF was 2x dx, right? So that's like 2x here. So this is like 2x dx, and so this will be x square, which if I after limit will be y square minus 0, which is y square overall. Okay, so this implies overall, if we summarize, okay, summarizing the CDF of y. Now, how does the CDF of y look like? So CDF of y look like now fyy. It's 1 if y is greater than equal to half. Okay, and it is y squared when 0 less than yeah, I can also include 0 because, okay, yeah, so 0 less than equal to y less than half, and it is 0 otherwise. Okay, so let us see. Yeah, so that's okay, right? So we have like CDF of y. If we wrap up, then this will be the case because y less than 0 is anyway 0, so I can include y. So cumulative, it is not affecting anyway. I can add 0 and nothing is changing here, right? So 0 can be included because less than 0 was anyway 0. So I cumulative add 0 and y half, and then for all of these I can put this into this. And if I go beyond half, then I must be like 1, because yeah, so that's where like I like beyond half, because the range is like half. So if I go beyond half, then the cumulative must be 1 beyond half. And any other value, in other words, like this otherwise case is equivalent to saying that y is less than 0. So these are the cases when the otherwise cases. Okay, so we can summarize this this CDF. Okay, so
Sir, can you again go through this solution? I didn't get what happened.
Which one?
This solution of solving the notion of mixed random variables or something like that.
Solution for the mixed random variable. Yeah, so well, I mean, you have to be specific, right? Asking
Like
for,
you gave the question, fx was given, and you were solving a CDF for y. So like in
yeah.
between, like what steps did you take? I didn't get like why, what happened. Can you just go through, skim through the solution which you wrote?
You okay? Okay, fair enough. So I can go revise it again. Yeah. So the problem is this, and I haven't defined mixed random variable explicitly. This is a motivation for going towards the mixed random variable right now. So so the way I am getting into mixed random variable is by defining a function of some some continuous random variable and then defining a function like this, and the CDF, it turns out that this as a function of x is no longer like a continuous random variable. Okay, so that's the motivation behind defining this. So this is the continuous thing. Okay, the continuous PDF. And so this will be continuous, and then I've defined a function of the random variable in this form. Okay, and then the question is find the CDF of y. And while computing the CDF of y, we will try to see what kind of CDF it is. Okay, so whether it was discrete, continuous, and so on. Okay, so that's the thing.
Is that function of y? Is it the PDF of y?
No, we want to compute the CDF. I mean, we want to compute the CDF. Sorry?
Is GX the PDF of y?
Yeah, so PDF is defined like this, yes, for y.
Okay.
Oh, no, sorry, no, no. It's not the PDF. It's just the random variable. Right?
Okay, sir.
Yeah, it's just the thing is like the way it is defined is like I can always fall back to the PDF of x to compute any probability that I am supposed to find. Okay, so right now it's a function of x. Okay, it's not the PDF. If we have to write PDF, I would have written fy y here. Okay, that's I have not written. So far, it's just a function of x, and along certain range is this, and along certain other range it's this. So look, I have already created a discontinuity here. So you can already see why the CDF is going to be discontinuous. If you look at this, then it's like x, it's like a linear going to like half and so on, and then okay, like is it like in terms of x, it's not looking discontinuous, right? But the point is like if I do 2x, then things change. Okay, so if I like plot this, then it's like 0, half, and yeah, so 0 to half, it is like a linear, so it goes up to here, and from half it's like this. Okay, so y itself is not looking discontinuous, right? So because up to half it took the value half, and from half onwards it's equal to half. So no issue so far here, but remember continuous were defined when the CDF was continuous, right? So that's what we are going to contract. What we are going to say is like the CDF of this is going to be discontinuous. Okay, so that's what we are going to. So to do that, what we did is actually computed the CDF. So first, since we are dealing with function of random variable, it's important to know what are the ranges when I have transformed from x to y. So the first step is to know what is the range of x. We clearly know the range of x is the values of x for which the PDF takes the positive values, right? So that's how the range of x is defined. So range of x is 0, 1 closed. And then for x in this 0, 1 interval, we know that gx, which is y lies between 0 and half. So we are computing now the range of y. So range of y is 0 and half. Okay, so for x in 0, 1, gx, because these are the all possible values x takes. So for all possible values, we have found what all possible values y will take, and this defines the range of. That's how we compute the range of a function, right? Now this gives the range. So immediately this tells me that anything below the 0, the lower range, must take the value 0. That's how the range is defined. And anything beyond the upper value of the range, it must be 1. In this case, the upper value was half. Okay. Now we went ahead and started computing the values of y, the CDF of y within the range. Okay, for the boundary cases we found out, and within the range, and I have singled out y equals to half because at y equals to half, at y equals to half, like this is an intuition here. I would say, like, why did I do y equals to half already? because at y equal to half, I suspect there is a discontinuity here, and which is coming out to be true here. Okay, because if y equals to half, then this means that like x is greater than, so y is equal to half. This happens only when x is greater than half, right? So this is the same thing as saying x is greater than half. So x greater than half means that I have to integrate from half to 1. Okay, because x takes the value 1 only, so there is no point in going up to anywhere else, right? So x greater than half to 1 in the range of x. Now, so we are like talking about PDF here, right? So PDF is like greater than 1, x is 0, right? So no point in integrating beyond that. Like usual definition tells us that it's half to infinity, but half to 1 only makes sense for x, otherwise 0 anyway beyond 1. So we restrict to 1 here. So half to 1, and then it was 2x. So 2x dx, and we integrate this, then we get 3 by 4. Okay, at y equals to half. So we are looking at the nature of this CDF, right? So at half, what we have is like 3 by 4. So somewhere it is 3 by 4 here. Okay, and we went ahead and looked at values of y for 0. So y greater than 0 and less than half. So FYY is probably that y less than equal to y. So these are all definitions. So, but for y between 0 and half, y is x. Okay, so these are the values of y between 0 and half. Okay, so y between 0 and half is exactly the identity with x. Okay, because y is equal to x. Okay, so y is equal to x for x value and half. So that's why I could replace y by x. So I replace y by x here, and so now this is asking for x less than equal to y. So I can do this again, like 0 to y, integrate this. So that's the definition, and then like the PDF I can put here, which is like 2x, and this is a valid PDF because x is lying between 0 and 1. Okay, so y is like 0 and half, so that's fine. Okay, so this is the PDF 2x dx, and if I integrate this, then this is y square. Okay, so the point here we are trying to make is like, so if we combine all this, then for y greater than equal to half, yeah. Yeah, that's fine. So for y greater than equal to half, we have 1. Like, okay, let's see. For y greater than half, look, for y up to half, what is happening in the boundary case, right? So y greater than half, we are sure that it's 1. So it is somewhere here, okay? So this is not yet 1, right? So this is like we are guaranteed that from here onwards. So there is a jump here, right? Now we are worried like exactly at half, like what happens, right? So greater than half, like we are sure this is 1. This is like given from here, right? So greater than half. So this is like it's not taking the 1 value. So I put a circle without solid circle, right? So this is like this. That is clear, right? And y less than 0 is 0, right? So this guy is also like confirmed. Y less than 0. So this is like the y graph we are doing, right? So and so y less than 0 is 0. Okay, and yeah, so y less than 0 is 0. Y exactly equal to 0. Well, it won't affect the CDF anyway because the singleton won't affect. So, and it is because it's kind of linear, right? So it doesn't matter, y square is also 0 at 0. Okay, so that's fine. There is no discontinuity here. And after that, it's like a it's like y square, right? So it will be like this, right? Okay, so at half, it's like y square, right? So it's like 1/4, right? So it's like 1/4. So it will not even go there, right? So at half, it will somewhere be here, let us say. So this is like 1/4. Okay, this is like 1/4, and at half. Okay, now we have to do the cumulative, right? So at half, it's 1/4 plus 3/4, right? So I think it will, yeah, it will make it solid here, right? At half, take 1, right? Because 1/4, because you have to do cumulative, right? So you went up to 3/4. Do I have excess space here? Yeah, so I have plotted this here actually. So let us analyze this, what happened, right? So this guy is 0, right? So that's what we need. Less than y less than 0 is 0. Y greater than half is 1. Y greater than half is 1. Now at y equal to half, it was 3/4, right? At y equals to half, it was 3/4. So 3/4, yeah. So 1/4 is there and a half is there. So 3/4 would be somewhere here, right? So this is the 3/4, which is the solid value, which is like, this is the case, this is the thing it's taking, right? And I'm not talking about the CDF. This plot is for CDF. I'm talking about this solid values for the PDF. So this is like the PDF, the probability that y is equal to, what was that, half? Yeah. So y is equal to, this is the probability value. Okay, don't take this as a part of the plot. The CDF will say that you have to sum up the values here, right? So the CDF will ask you to sum. So probably that this is like, I mean, sum all the heights, right? So this height, and then the sum of this height. That will be the CDF at half. So this is like 3/4, right? So cumulative up to here. So what height you achieved up to half? It is 1/4, and then after that, what additional height you could add? Okay. Yeah, it's getting a bit skewed, right? So this is like 3/4. But if I do the cumulative, then if I add this to height, then I am taken here, right? So 1/4 by 3/4, because in CDF I need that, right? So this goes here. If I have to plot the CDF, then this goes there. If I have to plot the PDF, then I'm here. But CDF says that you sum the height. So the CDF computed here will compute this height, right? So this height 1/4, and you augment, right? Because it's CDF. And from here onwards, you augment 3/4, so that it becomes 1, right? So fx at half, I can write this as fx x less than half plus, because this is like not continuous, I have to do this part by part. X equals to half. Okay, so fx less than half was 1/4. That's what we proved. And I mean, I'm talking about fx, but let us say this is like actually fy. Okay, so these are all y, talking about y here, and plus y at half was 3/4. So this was indeed 1. So that's why this solid color came here. At half, it has a jump, and otherwise it was up to 0, it was 0. After 0, it was following like a y square curve. So what do we conclude from here? We conclude from here is that CDF is not continuous. Okay, so CDF is not continuous in this case. So why is not continuous random variable? Because that was the definition of continuous random variable. A random variable is declared to be continuous if the CDF is continuous, not about PDF. Okay, it's about CDF being continuous. Okay, so CDF is not continuous, hence it's neither continuous. And CDF is also not in proper staircase form. Okay, so it's not even like a staircase like at each point in the domain, the discrete would ask for some staircase, like cumulative distribution function looks like a staircase. That is neither in a fully staircase form. Okay, at each value there should have been a jump or something like that. That creates a staircase, but that didn't happen. And so it's neither staircase nor continuous, and then that's why we classify them into mixed type. Okay, so it is a mixed random variable type. Okay, neither continuous nor, and there is indeed a jump at half. That's what we discussed right now. Okay, and the amount of jump is obviously 3/4. That's also we discussed. And CDF is otherwise continuous at other points. So it's continuous at this point. It's continuous at less than half, x values less than half. So that's the example of a mixed random variable. And I think we have to stop here, and we will do one more example on this in the next class, and that will be all. And then we move to multiple random variables in the next class. So I hope it's okay, and I can stop now. Okay. Okay then. Yeah. Thanks. Bye. Yeah. Have a nice day.